In this video, we'll learn about the processes of nuclear fusion and nuclear fission. We'll learn how these processes produce energy and how that energy is used to generate electricity in a nuclear power plant. Let's start off by exploring nuclear fusion and nuclear fission. During fusion, two or more lighter nuclei combine to make a heavier one. This is an example of a fusion reaction. During this reaction, four lightweight hydrogen nuclei combine to create a heavier helium nucleus and two positrons. This reaction is the net reaction of a series of more complicated reactions that occur in the Sun. Fission is like the opposite of fusion. During fission, a heavy nucleus is split into two or more lighter ones. This reaction is an example of a fission reaction. In this reaction, a neutron strikes an atom of uranium-235, causing it to split into lighter barium and krypton nuclei. This also produces 3 neutrons. This is the reaction that's used to generate electricity inside nuclear power plants. If you ever have trouble remembering which one is which, just remember that in fusion, nuclei combine, or fuse, together. Both fusion and fission involve changes to the nucleus of the atoms involved. In fusion, the nuclei are combined, and in fission, a nucleus is split. This means that both reactions are going to involve changes in binding energy, which is the energy required to keep the protons and neutrons in the nucleus bound together. Because of this, both fusion and fission release enormous amounts of energy. Both fusion and fission release millions of times more energy than burning fossil fuels does per kilogram of starting material. But if we wanted to compare the two, fusion reactions release about 4 times more energy than fission reactions do per kilogram of starting material. Fusion reactions also have other benefits compared to fission reactions. The fuel for fusion reactions, hydrogen gas, is much easier to obtain than uranium-235. Fusion also produces much less waste than fission does, and the waste that is produced is much easier to deal with. The fusion reaction is also much easier to control once it's started than the fission reaction is. So if nuclear fusion has all of these benefits as a source of energy compared to fission, why is it that we use fission in nuclear power plants? Well, as amazing a source of energy as fusion could be, it's unfortunately not a feasible source of energy production right now. The reason for this has to do with the fact that during fusion, positively charged nuclei must collide with each other in order to combine. But as we know, positively charged things tend to repel each other. So in order for these positively charged nuclei to combine, they need to be traveling at incredibly high speeds when they collide with each other. These high-speed collisions can only happen under certain conditions, when the temperature and pressure is very high. This is why fusion can happen readily in the Sun, where the temperatures can reach millions of degrees Celsius. So fusion is infeasible right now because it's incredibly difficult to maintain the necessary conditions for fusion to occur. Though we may one day be able to use fusion reactions to generate electricity, since this is a very active area of research. Scientists are investigating using plasmas and targeting lasers to maintain the fusion reaction. That's not to say that we've never created fusion on a large scale. This has already happened in the context of a thermonuclear bomb. A thermonuclear bomb first uses a fission reaction to create the necessary temperatures and pressures for the fusion reaction to occur. Since we can't use fusion reactions to generate electricity, let's see how we can accomplish this with fission reactions. Let's take another look at the reaction that's used to generate electricity in nuclear power plants. This reaction begins when a neutron strikes an atom of uranium-235. This produces barium-141 and krypton-92, as well as 3 more neutrons. Now each of those neutrons could strike another atom of uranium-235, again causing it to split into barium and krypton and producing 3 neutrons. And those neutrons can strike another atom of uranium, and so on. So fission reactions are capable of creating a self-sustaining chain reaction that can continue as long as there's neutrons and atoms of uranium. Maintaining this chain reaction is a large part of the operation of a nuclear power plant. If there aren't enough collisions occurring between the neutrons and uranium, the reaction will stop and we won't be able to produce energy. But if we have too many collisions, we run the risk of the reaction becoming uncontrolled. In the context of a nuclear power plant, an uncontrolled reaction is very bad. It can lead to the meltdown of the reactor core. But an uncontrolled reaction might be what we were going for if we wanted to build a bomb. We can control the chain reaction in a nuclear power plant through neutron moderation and neutron absorption. Neutron moderation slows neutrons down to ensure more successful collisions between the neutrons and atoms of uranium. Neutron absorption does the opposite. Neutrons are blocked or absorbed by some material, so it will prevent collisions between the neutrons and uranium. In other words, neutron moderation increases the number of collisions, and neutron absorption decreases the number of collisions. Now let's see how all of this ties in together to generate electricity in a nuclear power plant. Generating energy in a nuclear power plant starts with the fuel rods. Fuel rods are metal tubes that are packed with the fuel for the fission reaction, uranium-235. The fuel rods are placed inside a reaction vessel, which is called the reactor core, or just the reactor. The reactor core is full of water. The water acts as both a coolant for the reaction and a neutron moderator, so it slows neutrons down, ensuring more successful collisions. The last thing inside the reactor core is the control rods. The control rods are neutron absorbers. They are used to control the reaction in the reactor core. If the reaction is too slow, control rods can be removed so that fewer neutrons are absorbed and there are more collisions. If the reaction is occurring too quickly, more control rods can be inserted into the reactor core so that more neutrons are absorbed and there are fewer collisions. The fission reaction produces a lot of energy, which will heat up the water in the reactor core. The hot water is pumped into a boiler where it's turned into steam. Or the steam might be created inside the reactor core, depending on the design of the reactor. The steam is used to spin a turbine, and the spinning turbine is used to generate electricity in a generator. From there, the steam is pumped to a cooling tower where it cools down, so it can be pumped back into the reactor core to be reused. The operation of a nuclear power plant generates waste. The waste is things like tools used near the reactor core, the clothing of workers who worked near the core, and spent fuel rods. A nuclear power plant generating enough electricity to power the homes of about 1 million people will generate approximately 3 cubic meters of waste per year. In comparison, a coal plant generating enough electricity to power the homes of about 1 million people will generate 300,000 tons of ash per year and 6 million tons of carbon dioxide per year. So the amount of waste produced by a nuclear power plant is a relatively small volume. But nuclear waste is radioactive, so it needs to be dealt with carefully. The first thing that we do to deal with nuclear waste is to put it in barrels and store it underwater. We do this because fresh nuclear waste is extremely hot and quite radioactive. After the waste has had a chance to cool down, it can either be recycled or disposed of. If we recycle the waste, the uranium is extracted, mixed with fresh uranium, and used to create new fuel rods. But not all waste can be recycled. There's always some small amount, about 4%, that will need to be disposed of. To dispose of the nuclear waste, it's buried in barrels in deep underground caverns. Now, we've covered everything we need to know about nuclear energy, so let's practice our knowledge with a problem. What is the order of transfer of the electrical energy generated by nuclear fission from the fuel rods through a power plant? A. Fuel rods, generator, reactor, boiler, turbines. B. Fuel rods, reactor, boiler, turbines, generator. C. Fuel rods, boiler, turbines, generator, reactor. D. Fuel rods, generator, boiler, turbines, reactor. E. Fuel rods, generator, turbines, reactor, boiler. Nuclear fission is a type of nuclear reaction where the nucleus splits into two or more lighter nuclei. Nuclear fission is the kind of reaction that's used to generate electrical energy inside a nuclear power plant. This question is asking us to determine the order of transfer of the energy generated by nuclear fission through a power plant. In other words, the parts of the power plant that this energy goes through before it can be used to power our homes and businesses. And we're told that this process starts with the fuel rods. Fuel rods are metal tubes packed with the fuel for the fusion reaction, uranium-235. The fuel rods are placed inside the reactor. The reactor is full of water. The water inside the reactor will heat up because of the energy given off during the fission reaction. The hot water is turned to steam inside the boiler. The steam is used to spin a turbine. And the spinning turbine generates electricity in a generator. So, the order that the energy is transferred through a nuclear power plant is the fuel rods, the reactor, the boiler, the turbine, and finally the generator. This matches answer choice B. Now let's wrap up this video by summarizing what we learned. During nuclear fusion, two or more nuclei combine to make a heavier one. An example is this reaction where 4 hydrogen combine to make helium and 2 positrons. During nuclear fission, a heavy nucleus splits to make 2 or more lighter nuclei. An example of a fission reaction is this reaction where a neutron strikes an atom of uranium-235, causing it to split into barium-141 and krypton-92, which also produces 3 neutrons. Fission reactions create a chain reaction, which can be controlled to generate electricity in a nuclear power plant. The chain reaction is controlled by neutron moderation and neutron absorption. Neutron moderation slows neutrons down to ensure more collisions between neutrons and atoms of uranium. Neutron absorption blocks the neutrons from colliding with atoms of uranium to decrease the number of collisions.